How's it going, guys? Derek Craig with Oilfield Basics here. I'm in Houston, Texas, so I happened to be down here for the week, and Eric Allen from DynaQual reached out to me and said, hey, let's come do a facility tour. So what do you guys do here, Eric?
Yeah, well, thanks for coming. Again, when I saw you were in town, it was a great opportunity. You guys are doing great things with Oilfield Basics, so
thank you.
Wanted to give you the opportunity to see what we're doing here at DynaQual and how we're serving customers in this segment. So we are a fully functional reliability test lab. So a lot of our customers are people that are wanting to make sure their product can hold up, especially in the specific oil field market, downhole. And so we try our best to put their tools through the biggest stresses and make sure that they will perform downhole. So we have a lot of test apparatus to make sure that happens. And basically we're just taking their design unit, we're putting it either on a vibration table like we're going to see behind us, we're putting it through heat stresses, we're putting it through pressure, trying to just break it essentially. So we have a saying here.
It's a pretty cool job.
Yeah, no, we have a saying here that our founder Bob came up with. It's DynaQual, where being stressed is a good thing, and so we definitely put the engineers through the stresses here at DynaQual.
All right, well, sounds good. I'm excited to see the facility.
All right, so here we are in our vibration lab, and so in our vibe lab, what we're trying to do is take your unit, your test unit, what we call it is UUT, a unit under test. There's a lot of different words for that in the industry, DUT, all kinds of things, but your unit under test is what we're going to put on our table. So what we try to do is we try to mate it as close possible with our table here. And in this setup on our vibration table, we have a 2 foot by 5 foot plate, and this actually rests on a bed of oil, magnesium plate, to try and keep weight down as much as possible. We have 3/8/16 bolts, and we have all kinds of fixtures, as you can see on our walls everywhere, that mate to that table, and we want to try and get as close to a one-to-one representation between the fixturing and the unit that's being tested. The way we can do that is try and put accelerometers on it and make sure that our fixturing is proper, because when you're doing a test, especially in this kind of test apparatus, you want to make sure that it's as rigid as possible, because you want to put all that energy into the tool and try not to lose any through your fixturing.
So fixturing, you're pretty much referring to just everything it takes to bolt it down and secure it?
Yeah. Okay. So for example, a lot of our downhole customers use what are called split radius clamps. So you can see here that, and I'll actually put it on the table here. You can see here how we'd be able to put a unit through there. Pretty standard size, although there is really nothing standard about the different kind of tools we see. So we always have to try and mate up to the size of what our customer is looking for. And to do that, we have things like split radius clamps. So we'll take a clamp like this and we'll try to fit it to a customer's unit. So we'll put them in there, and that way we can have the proper fixturing to the customer's unit under test.
Okay. Is there a particular orientation that you have to let it lay
so
on the table?
Really, that is in this table here. Great question. This table here can actually rotate.
Wow.
So we can do, if people really need a vertical gravity axis, we call it, we take this plate off and we rotate up, and we got a 2 foot by 2 foot plate that we do for gravity axis excitation. So axis really depends on the customer, what they're looking for, and it's up to them to determine what their axis is. We really are here just to test what they want to have tested and make sure that it passed the certification that they're looking for. To that regard, there's different specs that people are looking to do, and that's the biggest thing we deal with all the time, is we see all the specs that anyone ever brings at us. So whether it's a standardized test or whether it's one that the customer's like, we believe that the downhole conditions in our drilling zone are X, and we try to represent that through our vibration in this table, through our heat and thermal conditions, through our ovens, and the axis is all up to the customer. So customers, like for example like this, they might determine this is X, we'll rotate it 90 for Y, and then we'll put it lengthwise for Z axis. Yeah, so this is actually an amp. So if you think of it like a speaker, that's exactly what's in here. It's an armature, and the armature translates that vibration to the table. So we have a whole bunch of modules, and of course this is an air cooled. There's also water cooled. So when we turn this baby up, it's quite loud to me. So of course we're able to plug a whole bunch of accelerometers in, And accelerometers are going to give you the different readings at the different locations you're looking for. A lot of our tools these days, of course, have accelerometers in them, but some customers come just to try and get an Excel characterization. So they want to see that their tool in their Excel that they have is set up for what we're inputting in. So we put in a 1-to-1, and they want to make sure that their Excel is seeing a 1-to-1.
Oh, okay.
So we can do that in a variety of ways, and we have a whole bunch of different accelerometers in order to do that. This, for example, is a great one. This is a triax accelerometer. So this is going to give you X, Y, and Z. Look at the size of that Excel.
Oh, man.
Some of our tools that we've done are pretty big. And so this is just a mate plate that will go on that. And this whole plate can also rotate, so we can do it X, Y this way. So we take these off and we rotate the whole table along here. And then customers want to have that XY acceleration, and so we put a plate on that. Well, you can imagine on the outsides it's just like a wing. So we have an oil reservoir, like I said, and so the magnesium is floating on top of that oil in order to make sure the slit plate can move in the displacement amount we need for vibration. So customers will want to see if there's any resonances within their unit. That's where we'll do the sine sweep. Customers want to make sure their unit will hold up to a certain spec. That's where we'll do a random vibration. And customers want to make sure during shocks that it's going to perform as well. So we can do all that using this. See it moving there?
A little build up.
There you go. So you got a whole bunch of displacement on the front end with a low frequency. So we're actually at only almost 10 hertz right now, and 3.5 Gs. And you see how it gets faster and faster. Again, in the sine sweep like this, we're going through all the frequencies to try and find a resonance. And so we might have different accels on it while we're doing this test to see if any of these frequencies have a resonance of any kind. And then again, as our frequency increases, you're going to see less displacement on the table. So it goes from being really high displacement. Again, that table has an inch on either side that it can move total. And so as you get higher frequency, we're moving less and less displacement, but our frequency is getting higher. So again, we're at 8.5 Gs right now and only 17 hertz of frequency. And so now we've reached 12 Gs, which this test is going to. And from 12 Gs, now we're just going to increase. It's going to be a flat profile from 12 Gs, and we're just increasing our frequency all the way up to 1,000 hertz. So you should, as it gets higher, you'll start to hear it whine. Just like anything that's in a high frequency pitch, you're going to start to hear it getting louder as that vibration gets smaller and smaller as the frequency goes higher and higher. This box here, actually, just to show you, is an oven for on top of the table. So we can actually put the product on the table, and then we place this oven heater box actually over top. We run two 6-inch hoses to our heater, and then we can actually do shake and bake, we call it, where we can do the downhole profile the customer's looking for, and then also give them a thermal output too. So 150 degrees and shock it, and vibration at a certain output. So that's where, if customers are looking for both, really trying to replicate the heat and the vibration of downhole, that's where a lot of customers will rely on something like this. This here is what we call a pneumatic shock machine. So just as the name suggests, it's a shock machine, and it uses air in order to pull the table down. The gravity helps as well, but it pulls it down faster in order to give you a certain G amplitude. So a lot of customers use this if they're looking for high G shocks. So we're talking about repeatable, and we just want to bang the thing up. So for example, on this, we've done 1,000 G shocks on this thing.
Oh, wow.
It depends on your duration you're looking for. So again, we're looking at that transfer and the duration that you can get, but we can get 1,000 Gs on this. We don't like doing it a lot because it's loud and it's big, but we've had big tools up here, and we're just dropping them in the Z-axis, and then obviously we're dropping them on the plate here as well. So real loud apparatus we have here. But again, customers that want to see that their tool will survive just real high amplitude shocks, this is a great apparatus to do that.
Yeah, I'm sure we get that in drilling a few times.
Yes, exactly. And so that's a lot of the stuff that's tested on here, stuff that you know is downhole and it's going to see a big peak shock. So we test those on here.
What's kind of like more of a common shock amount?
So a lot of customers want to make sure that they can, do 100 Gs, those kind of things. We can do shock on this table too. Mm-hmm. It's called the classic shock. So a lot of transportation qualifications call for like a 30 G classic shock with like a 10 to 11 millisecond duration. So we can do that on here for transportation qualification. So customers that have a box that they want to make sure can make it on a FedEx truck. That's a FedEx qualification. We can do that on here. It's not a kit box that they're sending to the field, because we know those shocks are maybe a little more. But there is a lot of stuff that we can do on this as far as classic shock goes. Mm-hmm. Whereas this pneumatic shock, again, is just a real high impact shock that we're doing.
Gotcha. And the shock, is it actually exhibited in the machine, or is it up on that upper plate?
Yeah, so what we're going to do is you can mount it same as that 4-inch centers up here. And we can mount the unit on here. And we lift it up, we raise it up, and then we just drop it like it's hot, as they say. And I could show you that quick too. So.
Yeah.
We put an accelerometer on the top here to try and read our readout. And then we tell it what we want it to do. And we can dial it in based on the height that we want the table to go. And then also we can put pads underneath to try and get the duration that we're looking for. So we lift it up, we start it, and it just prepares it. And then again, that air is going to help pull it down to get that kind of shock that the customer is looking for. So I've seen everything from repeatable 150 G shocks on this thing to, again, 1,000 Gs in every axis on a whole bunch of units. So depends on what the customer's looking for again.
Yeah.
This is a good product for just that impact shock. So it goes down and then it resets, comes back up to the drop height. It prepares for the drop. So right now it's filling up that air so it can suck it down, and then it's gonna go.
That's pretty cool.
So that's 664 Gs, just like that. And we can measure it and then plot it for the customer. And then again, say that wasn't where we want it to be, we can adjust it, either increase the PSI to get it a little more, increase the drop height. So let's go up a little higher. We'll do another one. So it resets, goes up to the drop height. It's going to hold and charge to the PSI level that we set it for, the charge pressure. It's going to hold at that for a minute. So again, that was almost 800 Gs. So if the customer wanted 800 Gs, and that's how we break things here at DynaQual.
Wow.
So this is our thermal lab. So again, in our thermal lab, we have 3 different chambers, a couple Russells where we can do vibration. A couple Russells where we can do humidity as well as dry environment. Yeah. So again, this is our Russell chamber, one of our thermal chambers that gives us the ability to do both heat and cold, and then also add humidity as well. So if a customer, for example, is operating in Baytown at a plant, we did a test just a little bit ago where they have a unit that's outside and they want to make sure that, let's say in Baytown humidity, that the unit will survive in the extreme temperatures that we get here in Houston. So we put the unit in here. We actually had standoffs for it so that we could try and get as much of that air around it. And then we can run power and monitoring through the sides here. And that way we can monitor the unit, power the unit, and see even what internal set points are. So we have thermocouples in there that obviously give us the export of what we're getting and the data we capture on the computer and give that to the customer. But then the customer can also capture their own data on their tests. So again, that's why everything we do here at DynaQual is about testing, optimizing, and giving the customer what they need in order to better their equipment. So again, humidity chamber, and then that chamber over there, same type of thing, except it's a dryer, so we can take out all the humidity and give it a dry environment. And so like, for example, on those, we test a lot of things like servers. Customers want to make sure that their computers will survive in a server room, and so we can do high heat, low temperature, make sure it comes back, those kind of things, or make sure hopefully it doesn't fail at all. So we're able to do a lot of that with our thermal chambers, and then some customers just want to bake their tools. So they'll say, hey, our standard, we want to have this thing in the chamber for 2 weeks, and we want to see what kind of if there's any failures in it, or if it survives the whole 2 weeks. And so we will put it in the chamber and let it sit for 2 weeks and see what happens at the end.
Okay. How do you demonstrate like that it's going to be reliable over time? So I mean, like you can do one test,
Right.
but how do you simulate that's going to be reliable in the long run?
So what you're talking about is more of life cycle testing. With life cycle testing, that's where we get into our Halt chamber here. So this is what's called a Qualmark Typhoon 4 Inferno, which is a really awesome name. It's a Halt chamber, which is highly accelerated life testing. And then it also does Hass, which is more of a highly accelerated screen. So a lot of customers, they want to first characterize their tool, which is what we'll use the Halt for. The customer is going to put their unit in the chamber. We're going to test a whole bunch of them and see what kind of levels it goes to. If we can get to a high temperature level, we're going to first start with that, and we're going to say, okay, this tool can get up to 100 degrees before it starts to see soft failures. We want to make sure it comes back from that, and once it comes back, we're like, okay, this is basically a soft failure zone. And then what we'll do is we'll go to the bottom end and do the same thing, and then we might try and take it to hard failure, where it won't come back. That way we know exactly, okay, this is a good zone to be in for operational, and this is a zone where we know we can't get up to. So let's say that's 150 degrees, and let's say on the bottom side that's negative 40. So now we have a profile of our tool can do negative 40 and 150 degrees. Over and under that, we're probably not going to work. But then we also want to make sure that it works at vibration too. So what we do is a vibration characterization. We start bumping up that vibration to make sure their boards are holding up. Again, this is more of a design level test unit. So if a customer has a brand new board that they're testing with all the new potting, accels, everything that's in there, capacitors, all that, we want to make sure that as a unit, the whole assembly will survive together under excitation. So this chamber here, the Halt chamber, gives us 6 degrees of freedom on our table. So you see this table moves like that. So there's a whole bunch of hammers underneath, and those hammers are hitting it up and giving us 6 degrees of freedom. So unlike our vibration table, which is giving us basically a one input axis, this is giving us that 6 degrees of freedom and really vibrating the entire thing. So we could put a unit using our same hole pattern, our 4-inch centers, over here, and we want to start bumping up that level to see how it goes. And so it's just going to vibrate that's the whole table to say 20 Gs, and we're going to hopefully get that table to find that soft failure again, where maybe the soldering starts breaking apart, but it's not completely. And that maybe bring it back, and we do the exact same thing with vibration as we do with the thermal testing. We want to get it to that point where we can characterize it as, hey, this is a good zone to operate in. Then what we do is a combined environment. So this is really where you're talking about how do we demonstrate over the lifetime of the product how it will survive. So through that Halt process with the thermal and the vibration and now a combined environment, we're really stressing this thing more than it ever would see, hopefully, in a lifetime, and trying to find out how long it would work. So that's where we try and correlate that to, okay, this is a good maintenance period in order to take them out of service. And different test specs have different ideas as far as how much vibration and heat and all that will degrade a unit. But we just want to get that characterization first, and then from there we can change that into the Hass process, which is the screening of your tools. So again, a lot of customers that come in here, they do a Hass, they do a Halt in order to characterize their tool, and then they're going to bring either all their products or maybe just a sampling of their products to make sure that they're maintaining those engineering standards. And in that, we're only going to take it not to that full level, which was failure. We're going to take it to half of that. So again, if their heat and their vibration was X, we're going to cut that in half so that we're not taking all the life out of the tool. And that way, once it passes here, it can still go into the field and not have to worry about it. So this is a Halt chamber. Nitrogen cooled 70-degree swings per minute. So,
Oh, wow.
yeah, we can get it real cool. Negative 100 to 250, like that.
Wow. And you can heat it up too?
Yeah. Yep. So we have a plenum on top that pours the heat in there, and like I said, 70-degree swings either way. So whether we're doing heat or we're doing cool, we're able to adjust it by 70 degrees per minute.
So why are the doors so thick? For insulation or
Yeah.
for pressure?
No. So this, again, it's a combined heat, thermal and vibration apparatus. Not pressure, of course, because we have the monitoring port still.
Oh, gotcha.
So we're able to put power the units, put power supplies on them, test units, and that way we can monitor and make sure that everything's good while it's in there. Of course, we can keep out as much of that air as possible so that we can keep it as sealed as possible. So
And don't get cold out here.
and of course,
Yeah.
it's a safety thing.
Oh, yeah.
So with all those hammers and everything going, we want to make sure these doors stay shut. So, and it would be way too loud if it wasn't. So it insulates it quite well. And a bunch of the safety systems rigged into it are to make sure that door stays shut and the product in there stays secure. So again, customers that have put a new tool into the field, this is where they should start after they've come up with a concept and they've come up with a design. Once they're ready to test it for field use, this is where they should be. And so that's why we recommend a lot of our customers, and a lot of our oil and gas customers have been here and have spent the time here doing the Halt testing to make sure that their boards hold up in that combined environment. It would be awesome if it had pressure too, because then we really would get everything, but we have another pressure apparatus for that. So I'm going to show you our pressure vessel now. We have a hyperbaric chamber. Again, we can either do oil or water in our pressure vessel. It's 30 inches deep by 6-inch OD. A lot of customers want to test their thing to pressure to make sure that it's sealed, and so a pressure chamber like ours will do that, either water or oil that we can test in, and that way after the test is completed, say they reach their pressure level, we dwell at a certain pressure level. If we don't see anything in the actual graph that we're plotting, because sometimes if there's a catastrophic failure, you actually see that pressure drop as it fills that void. The customer will take it and pull it apart later, and they'll be able to determine from there if there's been a failure. So again, we were doing a test today where something's in the chamber and we were going up to 20,000 PSI and sitting there and about 200 C, so it's quite a hot test, and now we're just trying to cool that unit off before we crack it open in the morning. So we'll come the next day, crack it open once it's completely cooled down and we have a nice profile on our graph, and bring the unit out and test it and verify that it works. So again, this is just our control room, and you can come in here and see we have Haskell pump system set up where we're able to actually pressurize the system. We have a display graph that we're able to export all the information from this and get it to the customer. So again, right now we're about 16,800 PSI exactly, actually, and 158 degrees Celsius inside. So again, really hot still and highly pressurized. So what we're trying to do right now is cool that down, and as it cools down, the pressure is going to go down with it. So that's what we're doing right now. So you can get a little look inside of our pressure room right there. And again, more than anything, it is completely sealed, but you can see by the 2x4s, we want to be as safe as possible. And which is why we have a door on there and why we have that room looking like a bunker. But customers will drop electronics in there, and we have a way to monitor the electronics through the top, so we can pull their power through and we can monitor it here on the deck and make sure that everything's working while it's under pressure. Motors, we test a lot of motors this way, do a lot of screenings this way, and then a lot of pressurized compartments people want to test as well. Well, it's rated, we've gone all the way up to 30,000, so we can go even higher. Now with heat, of course, we like to stay around the 200 degrees maximum, just because more than that, the oil that we use, our oil that we use, the flash point and all that isn't a problem, but it starts to break down with heat, obviously, over time. And so our oil that we use is made specifically for this exact purpose.